significant figures. Significant figures are the number of digits up to which we are sure about the accuracy of the value of any observation. Larger the significant figures, greater the accuracy in the result. Rules to determine significant figures. All non-zero digits are significant figures. For example, 2576 has 4 significant figures. All zeros occurring between two non-zero digits are significant. For example, 205076 has 6 significant figures and 1.0706 has 5 significant figures. All zeros to the right of last non-zero digit are not significant. For example, 205070 has only 5 significant figures. All zeros to the right of a decimal point and to the left of a non-zero digit are not significant. For example, 0.00562 has only 3 significant figures. All zeros to the right of a decimal point and to the right of a non-zero digit are significant. For example, 0.4580 has 4 significant figures. Addition and subtraction in significant figures. Suppose we are given x equals 6.342 and y equals 2.03. Then, now x plus y equals 6.342 plus 2.03 equals 8.372. In x and y, x equals 2.03 has least significant figures. That is 3. Therefore, the final result will also have 3 significant figures. Therefore, x plus y equals 8.37. Now, x minus y equals 6.342 minus 2.03, which equals 4.321. Again, rounding off to 3 significant figures, x minus y equals 4.31. Multiplication and division in significant figures. In multiplication and division operations, we retain the significant figures equal to those which appear in the last precise number involved. For example, if x equals 5.143 and y equals 2.03, then, therefore, xy equals 10.44029. Now, the last precise 2.0. Errors. The error in the measurement of a physical quantity is defined as the difference between the true value and the measured value, observed value of the physical quantity. So, error equals true value minus measured value. Types of error. The errors in any measurement are of 2 types. Systematic error, random error. Systematic error. The errors which occur according to a definite pattern are called systematic errors. Systematic errors are of 3 types. Instrumental errors. The errors caused due to faulty and improper working instruments are called instrumental errors. For example, if the zero of the vernier scale of a vernier calipers is not coinciding with the zero of main scale, the length measured by the vernier calipers will be different from its actual value. Personal errors. The errors in any measurement produced due to the mistake of observer are called personal errors. Natural errors. The errors produced due to the change in conditions of the environment are called natural errors. For example, if we are doing the experiment to verify Ohm's law, the temperature should be constant throughout the experiment, but if the temperature changes, results may differ. Random errors. Random errors are the errors produced due to unknown reasons and are sometimes called as chance errors. These errors cannot be controlled by the observer. These are constant in magnitude and can be positive or negative. Errors can be expressed in the following ways. Absolute errors. The difference in the mean value of a physical quantity and its observed value is called absolute error. It is represented as delta xi equals x bar minus xi, where delta xi is an absolute error of ith observation. X bar is mean value of the physical quantity. Xi equals ith observed value of the quantity. Mean absolute error. The arithmetic mean or average of all the absolute errors of the measurement are called mean absolute error. If delta x1, delta x2, delta x3 up to delta xn are the absolute errors of a measured quantity, then mean absolute error is delta x bar 1 upon n summation I, which equals 0 to n mod of delta xi. Relative error. The ratio of absolute error to the actual value of physical quantity is called relative error. Relative error, delta x, which equals delta x bar upon x bar. Percentage error. Percentage error equals relative error into 100%. Percentage error equals delta x bar upon x bar into 100%. Combination of errors. We calculate the error in the following possible cases. When the result involves sum of two observed quantities. Suppose two quantities A and B are measured to get the final result Z, such that Z equals A plus B. Delta A and delta B are the absolute errors in the measurements of A and B. Therefore, the measured value of A and B are A plus minus delta A and B plus minus delta B respectively. If delta Z be the absolute error in final result Z, then Z plus minus delta Z equals A plus minus delta A plus B plus minus delta B, which equals A plus B plus minus delta A plus delta B. Z plus minus delta Z is equal to Z plus minus delta A plus delta B. It implies delta Z equals delta A plus delta B. Hence, Z equals A plus B. Therefore, maximum possible absolute error in Z is given by delta Z equals delta A plus delta B. When the final result involves the difference of two observed physical quantities. Suppose two physical quantities A and B are such that Z equals A minus B. Let delta A and delta B are the absolute errors in the measurement of A and B respectively. Therefore, the measured value of A and B are A plus minus delta A and B plus minus delta B. If delta Z be the absolute error in measurement, this equals A minus B plus minus delta A plus delta B. This implies delta Z equals delta A plus delta B. It gives the maximum possible absolute error in Z. When the result is in the form of product of two physical quantities, let the result involve Z equal AB. The measured values of A and B are A plus minus delta A and B plus minus delta B respectively. If delta Z to be the absolute error in Z, then Z plus minus delta Z equals A plus minus delta A into B plus minus delta B. This equals AB plus minus A delta B plus minus B delta A plus minus delta A delta B. Since AB equals Z, therefore plus minus delta Z equals plus minus A delta B plus minus B delta A plus minus delta A delta B. Since delta A delta B is negligible, therefore delta AZ equals plus minus A delta B plus minus B delta A. Dividing both sides by Z, we get plus minus delta Z upon Z, which equals plus minus A delta B upon Z plus minus B delta A upon Z. This equals plus minus A delta B upon AB plus minus B delta A upon AB. Delta Z upon Z equals delta A upon A plus delta B upon B. When the result is in the form of quotient of two physical quantities, let the result Z equal A upon B. Let delta A and delta B are the absolute errors in A and B. Delta Z be the absolute error in Z. Therefore, Z plus minus delta Z equals A plus minus delta A upon B plus minus delta B, which equals A plus minus delta A into B plus minus delta B raised to the power minus 1. This equals A into 1 plus minus delta A upon A into B raised to the power minus 1 into 1 plus minus delta B upon B raised to the power minus 1, which equals A upon B into 1 plus minus delta A upon A into 1 plus minus delta B upon B raised to the power minus 1. Expanding 1 plus minus delta B upon B raised to the power minus 1 by binomial theorem. 1 plus minus delta B upon B raised to the power minus 1 is equal to 1 plus minus delta B upon B plus terms having higher powers. Neglecting the higher powers as delta B is very small. Z plus minus delta Z equals A upon B into 1 plus minus delta A upon A into 1 plus minus delta B upon B, which equals A upon B into 1 plus minus delta B upon B plus minus delta A upon A plus minus delta A upon A into delta B upon B. Delta A and delta B are very small, so delta A delta B upon AB is negligible. So, Z plus minus delta Z equals A upon B into 1 plus minus delta A upon A plus minus delta B upon B. Dividing both sides by Z, we get 1 plus minus delta Z upon Z, which equals 1 plus minus delta A upon A plus delta B upon B. Hence, Z is equal to A upon B, or delta Z upon Z is equal to delta A upon A plus delta B upon B. When the result is in the form of some power of a physical quantity, let Z is equal to A raised to the power n. Let delta A and delta Z be the absolute errors in A and Z respectively. If delta A is absolute error in Z, then Z plus minus delta Z is equal to A plus minus delta A raised to the power n, which equals A raised to the power n into 1 plus minus delta A upon A raised to the power n. This equals Z into 1 plus minus delta A upon A raised to the power n. Expanding 1 plus minus delta A upon A raised to the power n by binomial theorem of delta A. 1 plus minus delta A upon A raised to the n is equal to 1 plus minus n into delta A upon A plus higher power terms. As delta A is very small, we can neglect the terms having higher powers of delta A. So, z plus minus delta z is equal to z into 1 plus minus n into delta A upon A. Dividing both sides by z, we get 1 plus minus delta z upon z, which is equal to 1 plus minus n into delta A upon A. Delta z upon z is equal to n into delta A upon A.